Hello, and welcome to a new series of videos. In these videos, we'll be going over the importance that JAX has and the power that it provides to chemical engineers and engineers alike throughout the world. With that being said, let's go ahead and get started. So this is the problem we have at hand. We are given two tanks in series that have equal cross-sectional areas of 2 meters squared drain-through holes at the bottom, resulting in flow rates, and obviously meters cubed per second, from each tank equal to this little expression here. This will be coming in later. And then the first tank has two inlet flow, U1 and U2, and the flow rates are given as well as 2 and 0.5 meters cubed per second respectively. And then the second tank has, in addition to the flow coming in from the first tank, it has an additional inlet flow of U3, which has a value of 0.4 meters cubed per second. So, given this problem, let's go ahead and get started. Very first thing that we are given to do is determine the height at the steady state, right? So, first things first, I have gone and imported some valuable information, always NumPy, then JAX, and some other things I will be using, and then simplified some of them so we don't have to type all of them out later on. Some of these obviously you know, the root function, solve IVP, make subplots, we've gone over multiple times. So now the only new things is JAX NumPy, which is very important, and it'll help us out a lot, as well as scipy.signal. We'll go over that later on. But first things first, let's figure out the steady flow heights. The first things foremost, let's put in our AC, cross-sectional area, which is 2. And then I'm also going to give a value for alpha, which is going to be this little value out here out front, or 2, for our flow rates. So alpha is also equal to 2. And the other thing we know is the value for our 3 flow rates. So I'm going to call it U initial. So that's our initial flow rates, right? And I'm going to make an array for it. I'm going to call it through NumPy, or JAX NumPy. So jnp.array, very similar as what we would do with NumPy, np array, which just add a j out front, as we will be using JAX throughout this coding. And then our values, we have 2 for the first, 0.5 meters cubed per second, and 0.4 for the last. So there we have it. There are our 3 givens that we have at the moment, and now we can go ahead and proceed to determine how we get these values, right? So what we want to do is create a function. So as always, I'm just going to call it right-hand side. And then of course we want our dependent variable time, and then what we want to determine, h and our u, right? Then obviously, like always, we have to unpack these. So h1 and h2 is equal to h, and the same thing for u, u1, u2, and u3. Oops, is equal to h. U1, u2, and u3 are all equal to u. Right? Sweet. Then now what we want to do is create functions or equations for our flow rates, right? So I'm going to call it Q1 and Q2, right? It's going to be very similar. For Q1, obviously, it's going to be alpha multiplied by the square root of the height, right? So h1 times to the power of 0.5. And the same thing for Q2, we're just using h2, obviously, right? Alpha times h2 to the power of 0.5. Amazing. So now what we want to return is what the dh dt, right? So we want to return, and then I'm actually going to return it as an array, as we will pull it out later and use it for our root function, right? So jnp array, and we want to do what is coming into the first tank divided by the cross-sectional area, right? What's coming in is u1. I'm actually going to put this all in parentheses so it'll be easier. u1 plus u2, and subtracting q1 because that's what's coming out, right? and then divide all of that by the AC. That gives us dH1 dt. And then for dH2, we have obviously Q1 coming in, as well as the additional U3, and we are taking out Q2, right? The second flow rate, or Q2. And then divide all of that, divided by AC, right? And we should be good. Now we can go ahead and use our root function, right, to get our values out of this. So our root function, obviously, start off with lambda x. We want our right-hand side function, lambda, can't type anymore, okay, lambda x, right-hand side, and then we want our values, t, we're at the beginning, h is what we want to determine, x, or h, and then for our u, we have our u initials, right, u initial, right, and then once we need initial guess, I'm going to go ahead and say 0 for both, and we should be good, right? So it gives us a lot of information. Like always, if you want to pull out what we want x, we just do dot x. We get our values of 1.5625 meters and 2.1025 meters respectively for the first and second tank for the initial steady state height. And then we can go ahead and call this a function so that we can use it later on. I'm just going to call it h initial, because that is our height at our steady state when time is 0, so that we can go ahead and pull that out later. Sweet. So next step, we want to use JAX to linearize the dynamical equations with respect to the dependent output variables h1 and h2, and also with respect to the input variables u1, u2, and u3. So with that being said, let's go get started. Here what we want to do, so what we want to do here now is come determine our JH and JU respectively through Jacobian matrices. So what I'm going to do is start off with the height. So I'm going to call it JH, call it function, just because we will be using it to determine JH after. And then, like I said, JAX, and we want Jacobian. And then, of course, we want to put in what function we want to use and what arguments. So we want to use right-hand side, right? And then we want to understand which one we want. We are determining h, and h is 0, 1, index number 1. So we do simply just put 1. And that's all we need for Jacobian. Now we can go ahead and pull that out, as we just call JH is equal to JH function. And we put in our values for t, h, and u. So for time, obviously it's going to be 0 still. Our height, we got it here, our h initial. And same for our u initial, we have it here. So we can go ahead and put those in for our values, and u initial. And that is all we need. We can go ahead and put JH, and we should get our values in the matrices. Beautiful. So this is for respect to the first one and respect to the second one. Now we got to do the same thing with respect to, or for u, right? So pretty much the same exact thing. Call it a function again, and we're using Jacobian. And again, the right-hand side equation. However, we're determining u, and u is now 0, 1, 2, the second or index of 2. And then again, ju is equal to function, sorry. And then again, we put in our time 0, our h initial and u initial remain the same. Initial, and we pull ju, and we should get 3. Beautiful. So these are our 3 values for each respect to each height. So this is dh for dh1 for u1, dh1 for u2, and dh1 for u3, and the same similarly for these 3 values, but they're all respect to the second tank, h2. And it makes sense why u1 and u2 affect dh1, but u3 doesn't, and similarly to the second height. So now we've gone ahead and done this. What we want to do is use the signal.StateSpace function to obtain a linear time invariant representation of the set system. And we want to do this to set up C and D in order that we can isolate H2 as the only observed variable, so that we can determine H2 with respect to H2. So with that being said, we can go ahead and get started. We can simply signal.StateSpace. If we recall, signal, we just recalled it as sig. So sig.StateSpace should be a capital, I believe. Space, there we go. And then we have to put in our functions for A, B, C, and D values, right? So JH for our A, JU for our B, and then now we want to create values for C and D so that only our H2 is present. So what we want to do is create an array, obviously. So JNP, I believe, right? Yeah, JNP dot array. And we only want H2, so 0 for H1 and 1 for H2. And then we do the same thing for our D value, except we give them all zeros because our H2 is not in there, so we do not care. It's only for that, and then we should be good. And there we have it. There are our values all put into an array. Our A values, our B values, our C and D. And now we can go ahead onto the next step, which we want to use scipy.signal.StateSpace to transform the model into a transfer function between H2 and U3. And then with that being said, let's go ahead and get started. Let me just make sure this all looks good. Okay, so everything looks good. We can go ahead and use this signal SS2TF. Again, we use scipy signal as sig. So sig.ss2TF, which is for our transfer function. Then we're going to do similarly to what we did up here. We want our A, B, C, and D values. So for A, we want JH again. Our B, we want JU. And then our C and D, we're going to want arrays again. np.array. We're going to have the same values, 0 and 1. And then the same for our D. We're going to keep zeros through there. And then we want to put what input we want, what we want to determine, and obviously we want to determine our U, which is 0, 1, 2, our second input. That should be good. And then to pull that out, obviously we want to put in, call it something. So we'll call it numerator denominator, num10. And sorry. And then if we go say print num10, these are our values for our first array, and then for a second. And then now what we want to do is we want to create, turn this into a transfer function, right? For h2 and u3, so we're going to want to make this equal to h2 and, or I'm just going to call it h2 and u3 transfer function, right? Oh, simply a transfer function, right? So sig.transfer function, I believe. Yes, okay. And then we put num then, I believe. And then see what h2u3tf. I think it might be because I put J and P to be numpy. Why is there an array here? That shouldn't be there, so. Oh, wait, let me try calling this. So this is the limited time interval. There's something wrong with this expression. Oh, I think we're missing a bracket. Let's see if this does it. Maybe to both. Maybe just one. Okay. It worked before, right? Let's delete this. Okay, so it's because we have this array up front. So maybe I used Jax somewhere wrong. This might be a 1. Right hand side. What else? Oh, okay. I think I understand my problem. Let's see if that does it. Oops. Let's run this all. Hopefully this gets it. Nope. I already tried this, but everything looks good, so I'm wondering if it might be an issue of periods. Let me just see if that gets it going. Possible I need to split this up. Oh wow, okay, so it's literally just a matter of comma to get rid of those arrays. I apologize about that, but now we should be good to get our transfer function, hopefully. Yes, okay, yeah. So 0.5 and 0.2 is our numerator, and these are our denominators for our transfer function, right? So with that being said, we can go ahead and go on to the final step, which we want to create the step response of the linearized model excuse me, and compare that against the one that we obtained through solve IVP with the original nonlinear model. Okay, so with that being said, we want to determine, compare it against the solve IVP, so we need to pull that out and utilize that in this step. I don't like this being red. Okay. So we want to create a, what did you say? Sorry, the IVP. So we want to solve IVP. Function, I think our right hand side, right? Or I think we might need lambda out here. Lambda t comma x, I believe. I always misspell this. T-span, let's go 0 to 20. Now we're going to fix that up later. Or, go ahead and plug these in too. For our right hand side equation, again, we have time, height, and then u. So we want to use our t, right? H. No, I just want to change this to h just in case. Th, and then our u, we're going to use u initial, and then we're going to add an array, right, of 0, 0, and 1. Right. And then why not? We want h initial, right? Because that's the lowest it could be. And then our methods. We want the method to be Bordeaux, like always. And then what is the last? Dense output. We want that to be true as well. I don't think I need. Okay, I think that should be good. So I get a bunch of values for t and y. Beautiful. I'm just going to call this sol for our solution. All right, so we can use that later on. And I think I forgot a step before here, actually. We want to get this value for H2U32UF. How do you spell H2U3TF? We want to create a step function, right? So I think it's that step, oops. Step. I think we use H1, or we want H2 for the H2 derivation, and T, I believe. Okay, so now I think we should be good. Go ahead and plot this out. So like always, T plot and P dot line space. And then what we want obviously is H1 and H2 resolution, or I think we might need this. Right, we might get confused. For solution T plot, I believe. No, well, obviously it doesn't have any parameters. Let's go 0 to, what did we say? Did we already give it a value? No, just 20. So let's go 0 to 20, 100 points. Right. Then we should be good to go plot this. So fig dot make subplots, or make subplots. Fig dot add scatter. And then we want that for a second one as well. So for x, we want to use our h2 dev, I believe. Right? For y value, we want is this? Sorry, no. I think our x values is our t plots, right? And then x equals t for the second one, I believe. Y is equal to h2, I believe. And then the name, I think we can call this non-linear. Then t-plot, and then this is h2 dev from up here, right? And then we're gonna add the where is it? H initial. This value calling it with 1, first index, right? So plus h initial 1. I think that should be right for y, and then for name, this is going to be our linear one, right? I think that should be good. Shift enter, and no. Okay. I think it might be just as simple as changing these x values out, I believe. That might just do it. No. So this is, let's just try to see what comes out just with the first one. Nope. Okay. What about just the second one? Okay, so we got, the first one looks good, and we have an issue with the first one for h2 div and our h initial. Okay, so let's look at here, h2u3tf. Okay, so that looks amazing. Put that in. Highly conditioned filter coefficients numerator, the results may be meaningless. We get the correct values. These look correct, 2 and 3. Perhaps it's change these around. It should be t and h2. See if that does it. Okay, yes, there we go. So it's simply a matter of change 2 variables that were flip-flopped. So I was plotting it backwards. That's why that was messing up. So yeah, there we have it. This red one is our non-linear, and our blue one is our linear. As you can see, it starts about 2.1025. Excuse me, which is what we received up here. Just to show you again. That is our initial height, 1.5 or 2.1 for h2, and as you can see, our linear cuts off about, we start stabilizing about 10. As you can see, it only goes up by so little, and by the time it reaches 20, it looks like a flat out line, staying at 3.55 for the last 3 points. And then the nonlinear seems to be continuously increasing, even through 15 and throughout 20. So as we can see, this illustrates that the linear function is a lot more accurate, and we should be able to base our values off of it a lot more securely and safely compared to the nonlinear equation. Thank you guys for watching, and I'll see you guys in the next video.